At first, the universe was a vast, incredibly dense mass of issues. This mass underwent an influence that set into motion the particles, stars, and structures we can observe today. For a long time, physicists believed this to be the explanation for the universe's origin. However, recent research has introduced a different perspective, suggesting that the universe may not have had a single, clear beginning. Instead, it could be part of an ongoing cycle, with periods of expansion and contraction, potentially in a never-ending loop. Brian Cox, a renowned physicist, challenges the traditional notion of an ancient, infinite explosion. He argues that something cannot simply arise from nothing, which adds an intriguing dimension to the debate. Research from the James Webb Space Telescope has also uncovered evidence that contradicts the idea that the Big Bang marked the definitive start of the universe. This leads to the essential question: if the Big Bang wasn't the beginning, then what was? Join us on a journey back to the earliest stages of the universe, where we'll examine the edges of the Big Bang to find an answer to this question. If you're excited about staying informed on the latest discoveries about the universe and its mysteries, be sure to engage with our channel. Hit the like button, share the video, and turn on notifications. Astronomers have developed a detailed view of the universe's infancy, known as the Big Bang theory. According to this model, around 13.8 billion years ago, the universe was much smaller, hotter, and denser than it is today. In those early moments, all the components of our reality formed within a few minutes. In this theory, the universe, including stars and galaxies, was once as small as a peach, with an unimaginably high temperature of over a quadrillion degrees. This grand narrative has evolved with each new discovery. Astronomers have studied everything from the residual electromagnetic radiation from the early universe to the distribution of the lightest elements, and the evidence consistently supports the Big Bang theory. However, even with its solid foundation, we understand that this model is not the complete picture. There is still an unaccounted-for piece of the puzzle: the very origins of the universe itself. This challenge largely stems from the limitations of the current theories we use. The combination of general relativity and high-energy particle physics provides a theoretical framework, but it breaks down when we push it to its limits. When we delve deeper into the fundamental nature of the universe, the mathematical complexity increases exponentially, and our existing methods cannot provide satisfactory solutions. One of the key problems is the concept of infinite density near the beginning of the Big Bang, which seems almost impossible to comprehend. To address this, we need to explore new frontiers in physics and develop theories that can overcome these challenges, offering a more complete understanding of the universe's origin. Current models are not sufficient to tackle this issue, so we must look for new physical frameworks that integrate and explain gravity along with the other fundamental forces at incredibly high energies. This is where string theory comes into play. String theory attempts to offer a unified model that can explain gravity in conjunction with the other fundamental forces, especially at extremely high energies. Within string theory, the concept of an aeon emerges, named after the Greek word for age orb cycle. This idea suggests that the Big Bang, from our perspective, was the result of a previous event, meaning it wasn't the true beginning of the universe. Instead, it could be part of a continuous process. This leads us to the concept of cyclic cosmology, a theory that proposes the universe undergoes an endless cycle of expansions and contractions, each one following the other. This idea has been explored for some time, but string theory provides stronger evidence for it within its framework. In the cyclic cosmology model, the universe behaves like a never-ending series of collisions and contractions, stretching far back into the past and reaching into the distant future. Cyclic cosmology was first proposed by the famous physicist Roger Penrose, who was awarded the Nobel Prize for his work. Penrose was fascinated by a surprising mathematical connection between the early universe, which was extremely dense and powerful during the Big Bang, and the future state of the universe, which could become a cold, empty place with all matter dissipated. This theory suggests that these two states, though seemingly contradictory, are mathematically indistinguishable when extended to the extremes. Though this may seem paradoxical, the absence of matter in the future might be the key to understanding how all the matter we see today came into existence. According to this view, the Big Bang emerged from what remained after all matter in the universe had been consumed by black holes, which eventually dissipated into scattered photons in a vast void. The universe essentially arises from a state that is nearly nothingness. Yet this nothingness is still a form of something, a universe, though empty. The mystery lies in how a state so close to nothingness can lead to the creation of everything we observe in the universe today. The idea of continually generating new universes is an intriguing concept. Rather than viewing the origin of the universe as a singular, extreme event, it is now considered more likely that the universe is a dynamic, ever-evolving entity within a larger cosmic structure of inflationary development. Modern advances in speculative material science have also sparked interest in alternative cosmological models that challenge the standard view of a singular, limitless beginning. One such theory is the idea of a cyclic universe, where the Big Bang isn't a unique event but part of an endless cycle of creation, expansion, and destruction. In this view, the universe undergoes regular patterns of birth, growth, and annihilation, with each end leading to another Big Bang. This concept is inspired by both ancient cosmological ideas and modern speculative theories such as string theory. According to string theory, particles are not point-like but instead tiny vibrating strings of energy, and the cyclic universe naturally emerges from the theory's specific details. String theory suggests that the universe exists within higher dimensional spacetime, where cycles of expansion and contraction result from the interplay of fundamental forces. While the cyclic universe hypothesis remains speculative and faces significant challenges in terms of observational validation and theoretical consistency, it offers a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales. This model envisions a universe without a definitive beginning or end, where each cycle carries forward the remnants of its predecessor. Despite these theoretical models, observational cosmology has provided key insights into the early universe and its evolution over time. The discovery of the cosmic microwave background, CMB, radiation in the 20th century provided compelling evidence for the universe's origin, allowing us to glimpse the universe when it was only 380,000 years old. Detailed measurements of the CMB, from satellites like the Planck Observatory, have enabled scientists to map temperature variations and density fluctuations across the early universe with great precision. Observational cosmology has also illuminated the vast large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and massive filaments stretching billions of light-years. By studying the movement of galaxies and their redshifts, cosmologists have traced the universe's history, deduced its age, and predicted its future. One of the most remarkable discoveries in cosmology is the existence of dark energy, a mysterious form of energy that dominates the universe and is driving its accelerated expansion. First detected from astronomical supernova observations in the late 1990s, dark energy accounts for about 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The presence of dark energy poses a major challenge to our understanding of fundamental physics, as its origin and nature remain poorly understood. Some theories suggest that dark energy could be related to vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to explain the universe's accelerated expansion. Researchers are actively seeking new particles and interactions that might provide clues about the nature of dark energy. The Large Hadron Collider (LHC) at CERN, for instance, aims to probe the unresolved areas of particle physics by smashing protons at extreme energies, potentially revealing new physics beyond the standard model. Advances in astrophysical instrumentation have also allowed researchers to study the universe across different wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galactic evolution, and the distribution of dark matter. Looking ahead, future observatories like the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, are set to provide new insights into the early universe and its fundamental components. These cutting-edge instruments will allow scientists to examine the first galaxies, study the epoch of reionization, and search for signs of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the universe's origins represents one of the greatest scientific challenges in modern history. From ancient philosophical ideas to contemporary theoretical models and observational discoveries, humanity's exploration of cosmic origins has revealed profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge through new frameworks, technologies, and experiments, we are likely to uncover even deeper mysteries about the universe as both a virus void and a thick universe points to a deep and complex idea in cosmology, rooted in a mathematical process known as the conformal transformation. This process adjusts the size of objects while preserving their shape. Renowned physicist Roger Penrose demonstrated that the cold, void state of the universe and the hot, dense state could be connected through this scale transformation, adjusting their spatiotemporal properties despite differences in size. Penrose argued that time loses its conventional meaning in these extreme conditions, especially within the framework of cyclic cosmology. In this model, the universe transitions from an ancient cold void state to a hot, energetic state. The existence of the hot, dense state is considered the result of the previous cold, void state. But this relationship doesn't align with our usual understanding of time, since both size and time lose their typical significance under such conditions. In cyclic cosmology, the cold void and hot dense states exist on discrete plans, suggesting that from an internal perspective, within its own time frame, the cold void state could persist indefinitely. This concept ties physical science and philosophy together, offering speculative and structured explanations of the universe's origin. However, the question remains whether Penrose's ideas will be supported by future advances in cosmology. More fundamentally, the question persists: how did these cycles begin? This leads us to ponder the existence of something other than nothing, a key inquiry in understanding the origin of the universe. Three possible outcomes emerge when investigating the beginnings of these cycles. First, there may be no clear explanation at all. Second, there could be an infinite series of cycles, each representing a different universe, with the quantum state of each new universe being influenced by the universe that came before it. Finally, the third possibility suggests a single cycle in a repeating universe, where the beginning of each cycle is determined by some aspect of its own end. These scenarios are intriguing because they avoid the necessity of uncaused events and provide a more complex explanation within the framework of physical science. Penrose proposes the idea of an endless sequence of cycles, influenced by his understanding of quantum mechanics. In quantum theory, a real structure exists in different forms until it is observed, at which point it randomly collapses into one state. Penrose suggests that each cycle is shaped by random quantum events, leading to variations between cycles. This opens up opportunities for testable physics, as it implies the potential for detecting subtle imprints or anomalies in the residual radiation from the Big Bang. The quest to understand the origins and nature of the universe has long been a fundamental pursuit for humanity, from ancient philosophical speculations to modern cosmological theories. The study of astronomical origins has led to major discoveries and exciting speculative models that challenge our basic understanding of time, space, and matter. One of the most captivating questions has been the nature of the universe before the Big Bang. While the theory of the Big Bang provides a compelling explanation for the development of the universe from a hot, dense state to its present form, it leaves the question of what came before this event unresolved. This question raises profound philosophical and logical issues, pushing the limits of our understanding. Several speculative models have been proposed to address this, each offering unique insights into the early universe. One such theory is the concept of the multiverse, which posits the existence of many universes, each with its own physical properties and fundamental constants. According to the multiverse theory, our universe is just one among many, each emerging from different initial conditions and governed by its own set of physical laws. This idea naturally arises from certain interpretations of quantum mechanics and the theory of cosmological inflation. In inflationary cosmology, the rapid expansion of spacetime in the early universe might have given rise to pocket universes within a larger multiversal framework. Each pocket universe would have its own properties, shaped by random quantum fluctuations during the inflationary epoch. While the multiverse theory remains speculative and difficult to test, it offers a possible solution to the fine-tuning problem in cosmology, the puzzling question of why the fundamental constants of nature appear to be precisely adjusted to allow the existence of complex structures, such as galaxies, stars, and life itself. Another compelling challenge to conventional ideas of cosmic origins is the notion of eternal inflation, proposed within the context of inflationary cosmology. Eternal inflation suggests that the universe undergoes an infinite sequence of inflationary stages, each creating new regions of spacetime with potentially different physical laws. In this scenario, our observable universe is just one of countless regions within an ever-expanding cosmic foam. The idea of eternal inflation raises profound questions about time and causality in the multiverse, as each inflationary bubble could give rise to distinct realities with their own temporal and causal structures.